Welcome everyone for this last seminar of the academic year, so last SIPTA seminars. Thank you for being here. So thank you, Greg. Thank you, Gert, for being here, for giving the seminar as well. So and without further ado, I will let Gert introduce Greg. Gert.
Thank you, Seb. So, I was given the honor of introducing Professor Greg Wheeler, the pleasure, I should say. So, Greg obtained his PhD in philosophy and in computer science. It's a joint PhD at Rochester University under the supervision of Henry Kaiberg. And I think it's actually through Henry that Greg and I got to know each other. He went then on to postdoc positions at Nova University or New University in Lisbon. And then he also had a postdoc position at CMU in Pittsburgh and also at the Munich Center for Mathematical Philosophy at the Ludwig Maximilians Universität in München, of course, yes. And then after that, he became a professor of philosophy and computer science at the Frankfurt School of Finance and Management. He's also a co-founder of a financial software company. He's also the CTO of that company. So Greg, I think, is you could call him a polymath. He's active in quite a number of fields. He's also a great friend, and one of his great characteristics is that he is very opinionated. That's one of the reasons I like him so much. So, as I said, we originally got to know each other through Henry Kaiberg, but I think we got to know each other a lot better through the project workshops. Those were a series of workshops on the intersection between probability and logic that Greg for a long time helped organize, and that was I was fortunate enough to be invited to a number of times. And this is how we got to know each other a lot better, I think. It's also these project workshops, these project conferences that are, I think, responsible for the current rapprochement, if you want, between the SIPTA community on the one hand and those people in philosophy who are interested in imprecise probabilities or imprecise credences, as they or some of them would call them. I think today's talk is not about philosophy, although you could ask yourself the question, what isn't about philosophy? But it's more, I think, related to to Greg's current interests in finance. But I may be wrong, but you will have all the opportunities to correct me instantly as I'm now handing over the floor to you, Greg. Go ahead.
Thanks, Gert, for the very kind introduction. And it's a real honor to be here and to preview really the work that you'll hear probably next month in Bielefeld if you join, but of course in a more compressed form there. So I jump right into it. I think I've lost my shared. Share this again. Okay, there we are. So the plan is, since we have some time, I thought I would spend some time with you motivating the project, and because I think that can anticipate at least some of the choices that I made, and could maybe also get your help on, so if you kind of understand the sorts of examples and puzzles or issues that I was motivating the work. So there's really two pieces, and each of these correspond to the two papers that I'll be presenting at a SIPTA. So let's just jump into this with the first section I'm calling ergodicity breaking. So there's a kind of a classic example by Ponia, and I'll just describe this to get an intuition. So you start off with an urn, and it has two balls in it, one red, one blue. And the way the mechanism works is you randomly draw one of these balls. So it's like a coin flip. And whatever color you draw, you add for the next draw a ball of that same color. So if you draw red, then the next iteration, the urn will have two red balls, one blue ball, etc. And the interesting thing about this is that the proportion of red balls converges, say, to some value between 0 and 1, but that limiting value is random. And any value between 0 and 1 is equally likely as a limiting proportion. And so what we have here is an example where the expectation, the ensemble average, it's 1/2, but it's not representative of any individual trajectory. Or another way to put this is no individual urn or trace through one of these experiments represents the typical behavior. So this is an example, well, that's an example to sort of motivate, to get us started. You can turn this into, variations of this, like a sequential gamble that has more of a financial flavor, as Gert was mentioning. And let's say you have a gamble where the mechanism then is a coin flip, heads and tails. So the probability is fixed, but the payoff is that if the coin lands heads, it's a success. It increases your stake by 50%, and if it's tails, whatever your stake is at that point in the game, it decreases it by 40%. Now, if you take the expectation of this, the expectation value of this gamble, and again, the coin is fair, and let's say you start with 1 unit, €1, then you would expect to earn a profit of this. So the question is, should you stake €1 on, let's say, 30 tosses of this process? And you start running experiments, you start seeing things aren't turning out so well, you're looking at losses, and it turns out that the time average, the most probable value is that you would incur a loss. So there's this separation between the ensemble average, the expectation value, and then the average time average growth. So the upshot of these two examples is that expectation values don't always reflect what happens over time. And this is something that animates finance departments and people that participate in pricing equities. It's a foregone. It's just axiomatic. Everyone knows this. But it was news to me anyway, coming to a business school, and I wasn't really thinking about these kinds of problems, and they sparked an interest and approaches to modeling them, and also just to anticipate where we're going is one of the things I was interested in is that there's a property of these gambles, so it's not just your reticence or your attitudes towards uncertainty or risk, let's call it. But really, there's something you can get right or get wrong in the judgment of how the mechanism, the gambles are behaving. And that was something I was interested in, like, is to try to capture this property. And so that was one of the things that was guiding me in some of the decisions that, you'll see later. Now, it's not always that these things come apart. Birkhoff's equality basically characterizes when you can use expectation or ensemble values to get an estimate. So Birkhoff's equality just describes the conditions under which your expectation value of a repeated gamble is equivalent to the long-term time average of a single sequence of gambles. And something, I think I mentioned this in the 2021 the SIPTA paper, when I started thinking about these ideas, albeit it was a kernel of an idea. The dogma of ergodicity just doesn't question this, thinks that maybe this always holds, or they're just small corner cases that wouldn't ordinarily interest decision theorists. And that's, of course, that depends upon what audience you're speaking to, yeah, very much so. But I am exposed to some audiences in which this equality would never even be considered not to hold. So it's to those audience members that I address this dogma of ergodicity. So that is a brief motivation for this dynamics of of gambles and repeated gambles. And we'll return to this later in the talk about how to address how the framework that I'm going to propose will address these kinds of dynamics. Basically, how to handle multiplicative geometric growth over a sequence. So, okay, so if the first part is one of the motivations is dynamics, then the next I want to address is the varieties of discounting. So here's a quote. It's a historical quote. I won't tell you who it is initially, but you'll recognize the name. But if I read it out, it seems it's part of the rationality wars that were kicked off. People are seen to diverge from the standards of logic and rational choice, and so are they dumb, or is it something they're doing something more clever that's not being captured by our mathematical tools? And this went on for a good number of decades. But I'll read this. So it seems impossible to reach any definitive conclusions concerning human rationality in the absence of a detailed analysis of the sensitivity of the criterion and the cost involved in evaluating the alternatives, when the difficulty or the costs of the evaluations and the consistency or the error of the judgments are taken into account. In this case, we're talking about transitivity violating methods may prove superior. And this is Tversky. So Kahneman and Tversky were the architects for the biases and heuristics program. And that was a very productive and fruitful research program. But this kind of subtlety, I would say, was not a property of that research program. So, but it's something that's been taken up more recently, of course, in cognitive science, in the fast and frugal heuristics camp of Kurt Gigerenzer and his colleagues, but also empirically in animal studies and human studies. So you'll find preference reversals all over the place in the wild. So I'll just explain a couple of these. So this is a Canadian jay. So it's a bird in the North America. And this was an observation of, this is the experiment. You have rewards. So one raisin at a distance from the bird of 28 centimeters. So let's call this small reward, small distance. That's option A. Option B is a medium reward, medium distance. And option 3 is a large reward at a farther distance or large distance. And the birds will react with comparative choice of A to B, will prefer the small reward for small distance. Likewise, they'll prefer the medium reward at a medium distance over, comparing that to the larger reward, the larger distance. But if you pair option A to option C, they'll prefer option C. And so on, of course, classical rational choice theory, this is violating transitivity, would be scored as irrational or treated as irrational. But yet and this is what this paper by Waite does, shows that this kind of strategy is more prone to fitness. You have a higher probability of survival in Canadian jays from executing this kind of strategy. You see it in bees, so it's in birds, it's also in beads. In this case, the example was about artificial flowers. Again, you're seeing violations of transitivity or preference reversals. You also see it in slime mold, where IIR is violated. And you see it in people. So in this case, to tie this a little bit to some of the examples we'll be talking about, this was a study looking at discounting, whether to apply exponential discounting to, this is looking at future like savings or rewards, or hyperbolic discounting. So in exponential discounting, the main difference here is that the discount rate's constant over time, and you never get preference reversals from this. And so a feature of this. But hyperbolic discounting, the discount rate will decrease as the time delay increases. So, and it will regularly produce preference reversals. So to give you an example of this, these are scenarios that sort of explain the mechanics. If you had under hyperbolic discounting, if you had the choice between $100 and $110 today, most people would choose the $100 today. Whereas if you're looking at let's say a month or some farther off in the time horizon, you would take the preference would reverse. And it turns out that, again, this is another study that average Americans will live 4 years longer with hyperbolic discounting compared to, in this experiment with the observed experiment with exponential discounting. So I'm just mentioning a few of these examples. If you look for them, they show up all over the place. And there's a variety of ways you can discount rewards from gambles. We talked about hyperbolic. There's quasi-hyperbolic, so things are fixed at a constant at t0, but then thereafter there's hyperbolic discounting. You can generalize this. There's also kinds of discounting where it's scale dependent. So, the wealthier you get, the more risk appetite you tend to have. That's something that's observed. Also state dependent. And then there's one in the paper that I look at, which is constructing hybrid discounting. So, there's ways to construct mixtures of these other discounting rules. And these are basically the examples that I look at in the paper. And so I wanted to motivate them in the beginning rather than sort of show you the paper and what we're doing and then kind of walk through individual examples. The paper, I think, does that better than walking through that in a talk. So, okay, this is moving pretty quick. So we've done these two pieces, right? So we have ergodicity breaking, and I'll return to that at the last part of the talk and talking about dynamics. And then the varieties of discounting, the conceptual theme to attach to this part of the talk is preference change and potentially rational preference change. And more specifically, rational when you have some idea of so if you think of some of these examples where if you had you're fitting, so it's empirical in the sense you would be fitting some discount utility to, let's say, birds. But there's a normative standard you can apply, like, okay, the birds that are doing this have a higher probability of surviving, or life expectancy in this particular group of people tends to be longer. So it's empirical in the similar way that behavioral economics is empirical, but the idea here is that since we'll, as I'll show you in a minute, be able to separate belief from preference, there's a way to model this where you've encoded a normative standard. So even though you're deviating from standard expected utility theory, there's nevertheless, insofar as you accept the discount, the particular structure, the theory is encoding something that is you accept as a normative standard, then you can judge deviations from this as rational or irrational in a similar way that we're accustomed to. So there's a very normative, it's motivated by sticking to this desirability framework remaining a normative theory and not just sort of dragging it into another species of behavioral economics where we're adding parameters and fitting. Okay, so these are the motivating examples. Let me now then turn just to what is function coherence and sort of the main pieces of how the theory is working. So everyone on the call is familiar with the desirable gambles framework. So I'm taking the basic framework here, and theory of desirable things or sets of desirable gambles. So we're going back to the basics of Williams and Wally's version of this. I think this is the textbook version I either got from Gertz and Matthias's textbook or the introductory textbook. I'm not sure which one I've pulled this from, but I take this as just sort of the standard core theory for the coherent sets of desirable gambles. And so, one of the results is that if a set of, let's make them bounded gambles is coherent, satisfies these axioms, then there's going to be a functional, there's going to be a lower expectation that represents this set of gambles. And the thing I'm sort of wanted to focus on, again, at this high level, I'm setting aside deliberately the fuses that will come later to actually get the theorems to go through. But just conceptually at the high level, and one reason I really like this framework is that, at least to my mind, it distills so much down to just the elemental cores, right? So the first two axioms are rationality axioms. And you're basically orienting the scale for preference, what's up and what's down. And then the second pair are doing a lot of work. They're closure operators if you're thinking in terms of logic and constructing extensions. But the object that's being built is encoding the elements, the fundamental elements of a linear scale. And linear utility would be one instantiation of this. And so another motivation for this is like, oh, okay, so can we get away from this linearity assumption of desirability? So the motivations I was telling you earlier, but also sort of intuitive reflection, desirability isn't really linear. I mean, this is a simplifying assumption. What would it look like to be able to have more realistic models of desirability? So basically, the things we need to concentrate on are positive scale invariance and combination, right? So the idea is desired satisfaction is concave, but desirability, the technical notion, is linear. And it's down to these two properties in the set of axioms. So that's what we're going to focus on. To motivate this are not new ideas. I mean, going back to Bernoulli and the utility of wealth, he was, of course, proposing that we should always think of utility in terms of a store of wealth, and the changes in that wealth are going to be logarithmic. And you even see this. This is a nice example that I discovered, well, since moving to Frankfurt anyway. It's one of these empirical regularities that's so robust that it's called a law, and it's basically answers the question of what's the total volume of shares that are traded and the price impact. So if you have, like a mega investor like Warren Buffett dumping Apple stock, intuitively you think he's going to move the market by selling a large number of shares. And can you predict? And it turns out you can. And it's a square root relationship, square root of Q being the volume traded and the price impact that it has on the market. Okay, so what's this is my computer science operational way of thinking about these things is probably showing through, but the way I'm thinking of classical coherence is, you have linear operations on gambles, and there's going to be a representation by a linear functional, as we saw earlier, and it's going to encode really, and by encode I mean not entail, but the properties once you add the technical fuses to get you a utility function, but you're going to get no sure loss, you're going to get monotonicity, and the foundations, at least for a cardinal utility in your representation. So that's the classical coherence picture. And then the sort of the way I was thinking about or proposing for extending this, and it really is supposed to be an expansion, not an alternative. So you'll apply a transformation, and if this alpha is 0, then you just are still on track for a representation by a linear functional, so nothing is lost. But you're adding this parameter that allows you to get away from linear utility to nonlinear classes of nonlinear utilities to represent this kind of discounting I was mentioning earlier. And that's for when this parameter alpha is scalar takes some positive value. And so then we're talking about a class of sublineal linear functionals to represent. So that was sort of the big picture of, I was wondering what this might look like with the motivations that I mentioned before. And so that's the setup. So then what does it look like? So if you're comparing on the left our coherent set of desirable gambles and the function coherence, well, F1 is going to be the same, this avoiding partial losses. But instead of accepting partial gains, so monotonicity follows from this, but we're taking a monotonicity condition over here as an axiom. So if I'm using desirability or acceptance interchangeably for these purposes, so if F dominates G and G is in the set of desirable gambles, then F should be as well. So there's a monotonicity property of acceptance into the set or desirability. And then F3 is different. So that's getting at pieces of each of the scale invariance and combination. But we'll see later that there's another dimension of this, so we're going to need another axiom for these sort of dynamics that I was talking about earlier. But what F3 says is that for two gambles and a non-negative scalar, scalars lambda and mu, then basically we have when this function is defined, then H, this combination, this U convexity condition is in D as well. So this behaves as a kind of closure operator. So you'll get a convex cone out of this set. I've highlighted defined because there's some technical conditions in specifying what the conditions in which H needs to be satisfied, or I should say U needs to be satisfied in order for H to be defined, and I'll get to that in a minute. But that's the big picture for the first pass. So maybe I jump into that a bit more. So a couple of things. I'm presuming that this utility function, it's mapping from a set of bounded gambles into a scalar. So it's a utility function, assuming it's strictly increasing, continuous, and I add a normalization as well. So 0 gambles, 0 rewards. And then for F3, there's a couple of what well-defined this means is that so this map of X, the utility function to is the set of values for the set of values V, it's strictly increasing, continuous bijection onto its image. And F3B is that this image is convex. So for any pair of gambles, any non-negative scalars, the linear combination's always in the domain of the inverse of U. So with these two pieces, so this is basically spelling out what the conditions are for well-behavedness for this function. And then we get some properties from this. So you get non-triviality, so D is non-empty, and every F with positive utility is acceptable, meaning it's in the set, desirable if you like. It's upward closure. You could sort of anticipate each of these properties once you get the technical pieces in place. Transform convexity. So the U transform set is a convex cone. And transform variance for strictly increasing phi. Then this set of gambles in X that are positive under U tilde are also in the set of desirable gambles. So we don't have a representation yet. This is just properties of this these axioms with this notion of what we mean by the class of admissible utility functions. For a representation, there's just a couple of assumptions that we're adding. So one, we're assuming that D is non-empty and that D possesses a non-empty interior. So we're ruling out that you're going to have these infinitesimal gambles inside the interior. So if you have these two pieces, this R1 and R2 in the paper, in addition to the specification for F3, then there's a representation where there exists a continuous linear functional that maps from our values, set of values from the utility function to the real numbers, unique up to positive scaling, so that any gamble that's in the set, there'll be this composition of this linear functional applied then to the utility. So we're looking at the utility scale, whatever the result is, the image of this utility of a gamble. And of course, the evaluation of this needs to be above 0 or non-negative. And then the second result is that if we suppose X is a topological vector space and this utility function is continuous, then this acceptance set is an acceptance set D is just characterized by this property, and if Fn is a sequence of in D that converges to some F in X, then F is in the set of desirable gambles D. Okay, so there's 3 implications that I want to mention from this first set of results. I'm describing the first paper, and the title of the talk, the function-coherent gambles. One is that this no, I didn't put rho on the basically defining the risk, generalized risk measure. I can come back to this. I forgot to put this on the slide. It's this risk measure that's taking this composition, basically, of this structure. It's incorporating nonlinear utility. So you're getting a theory or an account for a generalized risk measure that instead of usually these generalized risk measures just have implicit, I mean, similar to the desirability framework, they would just have implicit this sort of linearity. And then by making this an explicit, making this utility function an explicit character, first class citizen, as it were, you have now a generalized risk measure that, incorporates this extension to nonlinear utility is the idea there. The next thing, which exercises the philosopher in me, I kind of like this idea, and I alluded to it earlier, is that you have this preference belief decomposition. So this composition of, you can think of L here as, or eta, or I can't remember the Greek name of this, is capturing the belief aggregator, and your utilities are encoding preferences. And there's a clean way just to separate these two things as their own objects. The other thing is you have order invariance. So relative preferences, not absolute risk values, determine choice behavior. And I think these are nice, attractive properties that are preserved in this framework. So what I covered in the first part of the talk is this function coherent gambles, that's one of the two papers that I'll be talking about, sort of the main paper, I guess, the foundation paper that I'll be talking about next month. And the examples I alluded to earlier, I mean, much of the paper is taken up with walking through the machinery for each of the examples to kind of get a flavor of how the account works. So I'm not going to do that here in the talk. I think that kind of thing probably goes better looking at it and looking at examples with pencil and paper in hand. Okay, so we're still in the function coherent world, but there's two pieces. And they map onto the two examples we were looking at before. So we have this that's covering an element of combination because, remember, the thing doesn't map exactly one-to-one because, I mean, this is the classical setup for this is synchronic choice, right? So I'm kind of applying it to a domain that it wasn't originally set up for. So that's because I'm emphasizing or interested in time. There's a couple of things that were going on in the first part, which is the combination axiom, that part in which you're constructing convex cones or constructing extensions, constructing objects. That piece was captured in F3 and the representation theorem, and allowing us to have these different non-linear utility functions covered by the representation. But there's another part of combination too, which I alluded to with the urn example and these gambles, where you're having dynamics that aren't additive. And that's the piece we need to address next. And so if you recall from the little example of whether this is the heads, you get a 50% increase on your wealth, or tails loss of 40%. And so the rule here that we're modeling is you're updating your wealth by this factor in a particular state after n independent repetitions. So the rule is going to look like this. And that describes a non-additive sequence, what I'm calling a sequence dynamics. So updates of wealth by this factor in a state, and then after n independent repetitions, your wealth will evolve in this multiplicative way. So the long run performance is determined by this geometric mean, or equivalently, by the time average of logarithmic returns. So this was the main motivator for the idea of introducing a nonlinear combination operator. And that's what I mean by gamble dynamics. So I'm not talking about process models or how preferences will change over time. It still is really in this desirability world. And how this is properties of gambles, if we're getting the right view of how the gamble is behaving. And it has this different dynamics than just additive over the non-log scale, I guess the original scale of the gamble. So, okay, so nonlinear combination this is the new axiom to add to the framework to cover this. So what we're doing here is you have a couple of gambles, and then there are nonlinear combinations specified by this. So the axiom just says if each of these gambles are in the set, then their nonlinear combination is also in the set. So for example, if you define a log return transformation, and this was the original example that kind of got this started in thinking about these multiplicative geometric mean dynamics, where you define this log return. This is the additive. This is the wealth generating dynamics we were describing earlier. Then their combination can be just treated as additive in the log domain. Okay, so yeah, that's the key idea. This operator converts multiplicative effects into an additive structure in the log domain. And that was like the kernel for this gamble dynamics part of the talk. So if we're looking at function coherence, then we have our axioms from before, also the F3A, F3B for spelling out what well-definedness means. All that's being carried over. This is our new axiom that we just call it nonlinear combination. Then we have a couple of results. First, to show that log domain additivity works as advertised. So if we have two gambles and there's a limit on the floor of losses, kind of like in real life. Well, I guess unless you're the Federal Reserve, but losses are bounded by below by, let's call it -1. I mean, I guess you could add credit and bankruptcy and other kind of mechanisms to this thing, but these are bells and whistles that would be extensions of something like this. So since you're operating on a store of wealth, we're just assuming all of the gambles across all the states are going to have greater wealth than -1. And that's just to get away from sort of these issues around zero. So this is also very much the computer science in me, I think, picking this value. So okay, this is assumed for all states, as all of these axioms are. These are evaluated point-wise. Then this is the log additivity rule that we were just looking at before. So that's a result. And then the main result is, does this new addition preserve function coherence? Where, again, all of the conditions that we applied to get our representation for F1 through F3, does adding the behavior of F4 preserve that or not? And so this is a result that suppose the acceptance that satisfies F1 to F3, also the regularity conditions, and F4, then there exists a continuous linear functional on a suitable vector space, looks like a typo, such that for every gamble, you'll be able to do this decomposition, where here we're looking at in the log domain for our utility function. Okay. So there are also some in the paper looking in the direction of generalizing this a bit. I mean, as I mentioned earlier, this geometric mean, this particular example is what got me interested, I guess, in this problem. I have a colleague in the department that works on systems these ergodicity braking systems. So that's kind of what got me into thinking about this. But a natural thing for the paper is like, okay, what would it look like to extend this a bit? And so there's some results in the paper for what a well-behaved combination operator looks like, and some properties of these things that I don't have in the slides, but I just will mention a couple of three basically classes of well-behaved utility functions that were looked at in the literature that emerge and what they look like in this setting. So there's power utilities. So the combination operator for this would look like this would be the form for a power utility. We've talked about exponential utilities before. This is something that Arrow studied, for instance. And this is what this looks like in with the combination operator. And logarithmic utility we were just discussing. This is all the examples I was showing were using this dynamics, and you've seen this before in the result. The risk, this is what the risk operators look like. I'm left off the other slide. there's an induced risk measure that you can get out of this too. So the earlier descriptions and the separation of belief and preference that I mentioned before carries over with this combination operator as well. And so we'll define an induced risk measure as a utility function with this well-behaved combination operator, where L is this the linear functional. And then we have some corresponding risk measures. So the power utility risk measure. What this is describing, so this will be a model for where it fits to where this thing exhibits decreasing relative risk of aversion. So under this power utility, an agent's risk aversion decreases as wealth increases. So you get richer, your risk appetite goes up. Exponential risk we talked about earlier as well, but it has this property of it exhibits constant absolute risk aversion. So it's recovering the entropic risk measure. So under exponential risk utility, an agent's risk aversion, it's just absolute, regardless of wealth. So if you were losing a penny is as painful now as it is no matter what your bank account is, or your bank balance is. And then logarithmic risk measure, again, just to circle back to why I was particularly interested in this, is that on the surface, it exhibits constant relative risk aversion, and it naturally captures multiplicative risk. However, it's like power utility, and that logarithmic risk aversion is proportional. So one way of looking at it on surface, it's similar, but conceptually, I would argue it's very different. So unlike power utility, logarithmic risk captures proportional multiplicative risk, that is compounding. And compounding is a property of the gambles, of the situation that you're in. It's not a property that's describing your psychological appetite for risk. You may have a different psychological appetite of risk and face one of these multiplicative risk gambles. And these two things should be, they can interact in interesting ways, but they should be separate. And that's sort of the main motivation for, conceptually at least, for approaching the problem in this way. And so what I was just describing is in the function-coherent gambles with non-additive sequential dynamics. This non-additive sequential dynamics is that combination operator, that O plus. And so that brings us really to the summary of the talk. And so we had two different motivations for this, for function coherence. I think one of the main conceptual motivations for this is this ability to separate belief from utility and construct risk measures that are sort of built on top of this. A lot of the discussion here, and even some of the compositional, some of these wild compositions of utility functions, I make really strong, precise probability assumptions, and that's just to make clear what's going on in this all this machinery dealing with these nonlinear utility functions. But what I think is kind of nice about doing this in the desirability space is that you have all of this capacity to investigate the interactions of this with uncertainty, and a really nice and attractive, I think, model for uncertainty. So if in my discussion today and also in the paper, I'm being very, very conservative with my examples, it is principally for expository reasons. But I think it could be a nice way to also introduce these broader set of tools to economics, and particularly this ability to model the processes and separate that from the psychology decision makers. So anyway, with that, I really thank you for your attention, and I welcome your questions.